This video will look at floating point binary arithmetic, adding floating point binary numbers together and subtracting them. Okay, so floating point binary addition and subtraction, the nice thing is it's carried out the same way as decimal addition and subtraction, what we already know. It's just a matter of ensuring that the points line up before we add and subtract, exactly what we were taught at primary school, I'm sure. So consider the following addition of two decimal numbers in standard form. If we wanted to add these two together, the first thing that we'd want to do is move the decimal points so that we have two numbers that can line up perfectly that we can then add. So 0.243 times 10 to the 2 means move the decimal point 2 places to the right, so that becomes 24.3. And 0.00112 times 10 to the 4 means move the decimal point 4 places to the right, so that becomes 11.2. Now we can add them. We can make sure that the decimal points are in line, and we can go from right to left, adding each column as we go. We end up with 35.5. And if we then want to put that back into a normalized index form, what we can end up doing is moving that decimal point 2 places to back to the left, so that the most significant value is just after the decimal point. And because we move the decimal point 2 places to the left, we need to make sure that our exponent reminds us of this, so we say it's times 10 to the 2. Now, floating point binary arithmetic is carried out, as I've said before, in the same way. So if you consider the following addition of two floating point 16-bit binary numbers, where 10 bits are given to the mantissa and 6 are the exponent, what we can do is the following. So we need to make sure that the decimal point is moved according to the exponent in each term, in each number, each value. So let's have a look at doing that. If we write that in a form that we recognise, 0.1101 times 2 to the 3 means move the decimal point 3 places to the right, so that becomes 110.1. Let's have a look at the second floating point binary number. So the mantissa we write down with the decimal point in the correct place. We say it's times 2 to the 4 because the exponent is 4, so that means move the decimal point to the right 4 places, so we end up with 1.1. Now we can add those values together. We ensure that the decimal points line up, and we add as per usual, and we end up with 1000.000 and so on. Now we need to make sure that we put it back into floating point form, but we need to make sure it's normalized. Now to put it into a normalized form, we need to make sure that the decimal point is just before the most significant value, most significant bit. So here we move the decimal point 1, 2, 3, 4 places to the left, so it's just before the most significant bit. So it's 0.1, and because we've moved it to the left 4 places, we need to record that as the in the exponent, so it's times 2 to the 4. And if we put that into proper floating point binary, where we have 10 bits for the mantissa and 6 for the exponent, we would leave it like this. Let's have a look at another example. So we're going to add the following two floating point binary numbers. Again, 10 bits for the mantissa, 6 for the exponent. So because the binary values are currently in floating point form, the position of the point needs to move according to the exponent before the numbers can be added. And remember, the point is after the first digit. So here is the decimal point. The exponent is 2, 1, 0. So we move the decimal point 2 places to the right, leaving 11.11. In the second value, floating point binary number, the decimal point is going to be moved 3 places to the right because the exponent's 3. So you go 1, 2, 3, and the value that we would have as the result is 100.11. We now can add those values together. We make sure that the decimal points line up. We work our way along, adding each column as we go. and then we can put it back into floating point form, normalized floating point form for our answer. Now, if this here is the result of the addition, 1000.1, that's not yet in normalized form, so we need to make sure that the decimal point is moved just before the most significant bit. So we go 1, 2, 3, 4 places to the left, and we then write down our exponent, or record our exponent as a power of 4. We can now write down our full answer in floating point binary, like so, making sure that the exponent is written as 4 in binary in 6 bits, and the mantissa 10 bits. So here's another example. Now what you might notice here is that the exponent of the first floating point number is negative. So let's have a look to see what that can become if we move the decimal point to get to the original number. So the decimal point is after the 0 in the mantissa. The exponent is -1. That means move the decimal point to the left 1 place. So it becomes 0.0111101. We do a similar thing with the second number. We find out what the exponent is. It is 4. So we move the decimal point 4 places to the right. So it becomes 1.000 and so on. 1, 2, 3, 4. So decimal point just after that 1. We can now add them together, make sure the decimal points line up, and then we need to make sure that we put our answer back into floating point form, or a normalized form. So the decimal point needs to move just before the most significant bit, so we move it 1 place to the left. So we end up with 0.10111010 times 2 to the 1, because we move that decimal point to the left 1 place. And now we can put it back into the floating point binary form that the question started off with, where it's 16 bits, 10 bits for mantissa, 6 for the exponent. So we put the power of 1, or the exponent of 1, into 6 bits, and the mantissa we write down as it's 10 bits on the left. Okay, so subtraction, done very much the same way. We just need to remember that when we subtract, we are adding the second number in its negative form. So consider the following subtraction of 2 floating point 16-bit binary numbers, again 10 bits of the mantissa and 6 for the exponent. So if we want to take away that second value, let's first of all have a look to see what those values are after we've moved the decimal points according to the exponents. So the exponent in the first floating point number is 3, and it's 4 in the second one. So if we move the decimal point 3 places to the right, in the first value we get 110.1, and if we move it 4 places to the right in the second binary floating point binary number, it becomes 001.1000. Now, because we're doing subtraction, we need to convert that second number to its negative equivalent using 2's complement. So if this is our value, we need to flip the bits and then add 1. And if we flip the bits, we get this. If we then add 1, we get 110.1000. And now we can add those values together. So we line them up, make sure the decimals in the right positions, one under each other. And we do our addition, and this is the answer that we get. Now ignore the the overflow. Okay, we can treat that as a 0. So to put this back into normalized floating point form, we need to remember to move the decimal point so that it's just after that 0, or just before the most significant bit. So we move it 1, 2, 3 places to the left. So we can write down our answer as 0.101000000 times 2 to the 3. And if we want to put it down into all into binary, we need to make sure that the exponent 2 to the power of 3 is written in those 6 bits, like so. So the 3 there is written in binary in 6 bits. Now it says here, always ask yourself the question, is the second number bigger than the first? If it is, you know that after the subtraction the answer will be negative and in 2's complement. Remember, if you take away a larger number from a smaller number, the answer will be negative. If it's in 2's complement and we want to be able to read that, we may need to convert it back, and that might be handy in this next example. So this is the subtraction. It's difficult to know which one's larger, so let's make sure that we move the decimal point according to the exponent so that we can find out what those values are. So the exponent in the first is 2, in the second it's 3, so we move the decimal point 2 places to the right in the first, and we move the decimal point 3 places to the right in the second value. So these are the two numbers that we are now going to subtract. Now because it's a subtraction, we need to make sure that we convert the second number to its negative equivalent using 2's complement. So we get our value, we flip the bits, we then add 1, and we end up with 1011.0100000. And now we can add them. So if we make sure those decimals line up, we add our number, which effectively is a subtraction, and we end up with this value as our answer. Now remember, if you look up here, we are taking away a larger number from a smaller number. The answer is going to be negative. So this here, this number is in 2's complement. Now if we want to make sure that it is then represented in a normalized fashion, the decimal point has got to be just before the most significant bit. Now in 2's complement, if it's a negative number, the most significant bit is this 0. So it's effectively already normalized. So we would write down our answer with 10 bits for the mantissa as 10000000000 times 2 to the nothing. And obviously the exponent should be written in those 6 bits to finish off our 16-bit floating point binary number. So that is how we would represent the answer in a normalized floating point binary form.